Hello, and thank you for joining me. My name is Christian DeLucia, and this video is on null hypothesis significance testing. Inferential statistics like the independent samples t-test use sample data to infer conclusions about populations, and null hypothesis significance testing remains the primary way in which these inferential decisions are made in psychological research. So today's slide set is going to introduce you to some concepts and act as a primer for the procedure. Here are some relevant elements. First, statistical significance, which itself subsumes many concepts. I've listed a few here. Criterion for statistical significance, or the alpha level, test statistics, P or probability values, decisions about the null hypothesis, different types of errors researchers can make. And then when you're working with null hypothesis significance testing, it's also important to keep these additional elements in mind: sample size of the study, magnitude of effect, confidence intervals, and statistical power. Here are a few steps that I recommend to students first learning about null hypothesis significance testing. First, write out your hypothesis using words. Next, translate your hypothesis from words to symbols. In doing so, you actually create two hypotheses. Declare or define the criterion for statistical significance, which is referred to as the alpha level. Run an appropriate analysis and make a decision about the null hypothesis. Compute a relevant effect size estimate. Compute a confidence interval around the effect size estimate. And then based on all of that information, interpret your results. So here's an example of a written hypothesis. Students majoring in psychology will have higher levels of empathy than will students majoring in engineering. This hypothesis, or hypothesis like this, is often referred to as the researcher hypothesis, and it typically translates quite nicely to the alternative hypothesis that we're going to talk about in a couple seconds. From the researcher hypothesis, it's typically easy to work backwards towards the null hypothesis, and this is the process that I recommend for students. So in this slide, we've taken our alternative hypothesis, derived the null from it, and then translated those hypotheses into symbols, as you see here. So if we look at the alternative first, we see mu sub p is greater than mu sub e. The p and e there stand for psychology and engineering students, respectively. Mu is the population parameter, population mean in this case, denoted by the Greek letter mu. Under the null hypothesis, we see mu sub p is less than or equal to mu sub e. Some observations about the null and alternative hypotheses. These hypotheses are written using population parameters. Remember, inferential statistical procedures use sample data to infer conclusions about relevant populations, and that's why we write the null and alternative in terms of population parameters. These parameters are unknowns. We're going to use our sample data to provide estimates of them, but they're unknowns. The null and alternative hypotheses are mutually exclusive. The alternative hypothesis in this scenario is directional, although it's more common to have non-directional hypotheses in psychological research. Next, we're going to talk about the criterion for statistical significance, aka alpha level. The industry standard for alpha is 0.05. You might see less conservative alpha levels of 0.10 that are used in preliminary or pilot work. You might also see more conservative alpha levels of 0.01 or 0.001, and those more conservative estimates are used for lots of different reasons. Next, we're going to run an analysis and make a decision about our null hypothesis. In this hypothetical scenario, we could use an independent samples t-test, which is one of many inferential statistical procedures that can be used to test the difference between two population means. So here we've got a write-up and decision about the null. So our first statement provides a little context. An independent samples t-test, alpha equals 0.05. One tail was used to examine whether psychology students report higher levels of empathy than do engineering students. Results were statistically significant and in the hypothesized direction, in that average levels of empathy were higher in the psychology students than in engineering students. Next, we have some technical statistical information. The way we would read that is T on 158 degrees of freedom equals 3.16, P equals 0.001, and that's a p-value from a one-tailed hypothesis test. So T is just the name of the test statistic in this case. 3.16 is just the value of the test statistic. And then P in this context is short for the word probability. This is just telling us the probability of our test statistic given the assumption we made under the null hypothesis. These results are statistically significant because the p-value from the test statistic is lower than our predefined alpha level. In my experience, students often confuse the p-value from the test statistic and the alpha level or the criterion for statistical significance. It's very helpful to keep those things separate. Remember, we set our alpha level, our criterion for statistical significance, prior to running our analysis. And then when we get our p-value from the analysis, if it is lower than the criterion for statistical significance, we will declare our results as statistically significant. It's also common to include some relevant descriptive information, and means and standard deviations would work well in this context. I didn't do that because this is just a hypothetical example. What statistically significant results indicate? Okay, so here we're going to reject the null hypothesis that average levels of empathy in our hypothetical population of psychology students is less than or equal to average levels of empathy in the hypothetical population of engineering students. This decision to reject the null hypothesis hinges on the idea that our sample data would occur relatively infrequently, in this case less than 5% of the time, p less than 0.05, our criterion for statistical significance, if the null hypothesis were true. Okay, what statistically significant results do not indicate? They don't indicate that the probability of the alternative hypothesis is true. We can also say that non-significant results do not give us information about the probability that the null hypothesis is true. Students often make those mistakes, so be mindful of that. Statistically significant results do not indicate how likely the results are to replicate, even though that would be very useful information. Statistically significant results do not indicate that the results are substantively or clinically meaningful. Again, students often regard those concepts, statistical significance and clinical utility, as synonymous, but they are not, so be mindful of that. Some additional useful information that one can provide when describing results from inferential statistical procedures. It's very helpful to report an effect size estimate. Cohen's d would work very nicely in this case, and I like to report confidence intervals around the effect size estimate. Typically, if we have the criterion for statistical significance set to 0.05, we'll report a 95% confidence interval. And in intervention studies, it's useful to provide some indicator of clinical utility. In clinical psychology, which is my home discipline, it's common for researchers to report information like the percentage of clients no longer meeting diagnostic criteria in the intervention condition relative to the control condition. Anytime we're using statistics to make inferences about populations, it's worth it to stay humble. Whenever we reject the null hypothesis, it's possible we've made a type 1 error. Type 1 errors are rejecting a true null hypothesis or finding an effect in our study that does not exist in the population. Okay. It's also worth it when we're using null hypothesis significance testing to be mindful of the association between sample size and statistical significance levels. All other things equal, larger samples result in smaller p-values. And this association between sample size and statistical significance is particularly salient in smaller sample and larger sample contexts. A few final thoughts. Stay boring with your language. Use the terms reject the null when describing statistically significant results and fail to reject the null when describing results that are non-significant. If you stick to that boring terminology, you're less likely to inadvertently make a logical error like some of the ones presented on prior slides. Report exact p-values from your test statistics unless they're very small, in which case it's perfectly acceptable to truncate them to p less than 0.001. Report effect sizes and confidence intervals around the effect sizes for all primary results, regardless of statistical significance status. I often see when I'm reading published manuscripts that the authors will provide confidence intervals and effect size estimates and confidence intervals for results that were statistically significant, but fail to provide that information for results that non-significant. It's actually helpful to report that additional information in both contexts because it provides some useful practical information for the reader. The final point here, using null hypothesis significance testing can be part of interpreting your results, but should not be the only part of interpreting your results. When NHST is used in isolation, an unnecessary information void is created. Here are some additional resources for this and related topics, and these are some of my favorite resources. Thank you for watching the video. I hope you found it useful.